Ladies and gentlemen, you may remember this video or perhaps this other video from my Instagram feed, that is, if you follow it. Basically, in these videos, I am sort of pedaling on a stationary bike, and it is actually advancing the screen on Google Street View, which is a cool way to cycle and not go outside at the same time, which is kinda two things I want. Today, let's take a look at this particular setup and just try to understand what is going on there, and to look at the very simple code that powers the entire thing. You're watching another Random Wednesday episode on 0612 TV. Hello and welcome back to another Random Wednesday episode. So, today we're going to be talking about our exercise bike project. This is a, fairly deep project in the sense that it has sort of hardware and software components. However, you'll find that the amount of work that actually goes into it is fairly little. You don't really need to know or do a whole lot because, most of it is really simple. We're going to start this episode by having a very brief overview of the entire project. Then we're going to go into the hardware and software aspect separately. So let's start with just a very brief overview. Of course, I didn't build the stationary bike itself. That was a purchase, I just made online. It's a fairly cheap exercise bike. Basically, it's one of those that is, just the pedal portion. And yeah, you find any old chair and then you sit down at it and you pedal away. Now, this one actually comes with its own monitor, which will actually give you some information about how long you've been pedaling for, how many calories you've burnt and things like that. But of course, I would like to build my own because, that's how everything starts, right? So what we need to do is to figure out some way to, devise when we are pedaling and to make use of this information to generate everything else, be it statistics, be it some means of controlling Google Street View. And that is where the Arduino comes in. It talks to some sensors, it picks up the position of the pedals, and at intervals, it shoots out messages via serial, which of course is communicating over USB. These messages are listened to by a program on the computer, which can then do things like generate GUI or send keystrokes to something like Google Street View. That basically is the long and short of it all. And what we're going to do now is we're going to look into each part, firstly the hardware aspect, and then the software aspect. So let's begin with the hardware aspect. As it turns out, the magic that makes it all happen is the read switch. Now, we've taken a look at the read switch in an earlier Friday Minis episode. You can think of it as simply a magnet detector. When a magnet comes close by, the switch closes, allowing current to flow. My original setup that you've seen in the two videos, from Instagram, actually just had one read switch. So essentially what I've done is I've attached a magnet to one of the pedals and a read switch, somewhere nearby, right? Because we know for sure that the magnet is going to go around like this. And of course what that means is if at any point of time along the way we have a read switch there, when the magnet comes close enough, it's going to close the switch. And that is going to, of course, send off a tick to the Arduino itself. Right now I've actually enhanced the setup a little bit. Now I have two read switches. In fact, my setup looks like this. It is a half-size breadboard with an Arduino Nano, as well as two read switches on each side. Of course, what that means is I need to have one magnet on each pedal, and as a result, I'm able to detect every half turn of the pedals, because of course, every half turn, one of the magnets are going to come near one of the read switches. Of course, I have these on different pins, so I'm able to find out whether it's the left pedal that's down or the right pedal that's down, and that's of course really nice. And yeah, using this information, all I need to do now is to write a little bit of Arduino code to send off a signal to the computer whenever any one of these magnets actually pass by the read switches. I opt to do it this way instead of having, the Arduino do all the work, because, I want to be able to generate my analytics and to actually display a nice GUI on my screen. So that's why, it's kind of roundabout. If you use something like an Arduino Leonardo or any one of it that has a USB controller right on the Arduino itself, you can technically write all the code on the Arduino and it will send up a key press that moves your Google Street View forwards. In fact, that part is just pressing the up arrow. So yeah, that could actually be made very simple. But in this particular case, I'm splitting it into two parts because I want to potentially do more. So let's take a very quick look at our Arduino code. It's just a couple of lines, and you'll see how easy it is to actually detect the magnets coming in and when is the right time to actually send up a message. Let's take a look. Let us begin first with the simplest possible version of the code. Well, this is just 20 lines and is technically enough to get things going, even though it's not quite great. Let's take a look at what we're doing here. First, we use constants to define our two sensors, the pins for them. In this case, I have the left sensor on pin 3, the right sensor on pin 2. When I set up the program, I basically set both of these to be used as input pins. In addition to that, I switch on serial communications, and this is of course important because, well, your Arduino needs to send a message over to your computer. This is all we need to do for our setup. Moving on to the loop itself, in this particular iteration, all we need to do is to first read the left sensor. If it reads high, then we send out the message left to the computer. If it doesn't, we'll check the right sensor instead, and if that reads high, we'll send the term right. Of course, if the pedal is in neither one of those positions, we can just send none. Essentially, when we do things this way, our Arduino isn't doing any processing at all. It's just sort of reading from the sensors and sending everything back through to the computer for further processing. Now, this works. If we look at the output from the console, you will see that indeed, as I pedal, you will see, the occasional left, the occasional right, and a lot of nones in between. But there are of course a lot of drawbacks to this because, well, you're sending a large volume of data to your computer. Since the Arduino itself is capable of, well, some processing power, let's harness that and do more with our Arduino so that the information that ends up on our computer is cleaner and easier to work with. So this is a slightly improved version of the program. By just adding a couple more lines, we can drastically reduce upon, well, the information that the Arduino needs to send to the computer. Here's what we're doing. Now, most of this is actually the same, right? The setup isn't very different, but notice that we have introduced two variables here, which actually represent the last known value on the two sensors. We initialize both these values to low. The reason why we're doing this is because we want to be able to detect when the state changes from low to high. That is of course the moment when the pedal actually enters within the range of the sensor. That is when we want to send out just one message that says, hey, that pedal has come in range. It will not send out any more signals until the next time the pedal comes close again. What this means is we'll only send out our left and right signals just once per pedal entry. Here's how we do it. We read from both our sensors and we basically check. If the current value for whichever sensor it is high and its last known value was low, this implies that its state has gone from low to high, and that means previously the pedal wasn't in range and now it is. Because of that, we send out the message left or right depending on which sensor it is. Of course, when we're doing things this way, we must always take care to update the variables the moment we're done with them. The previous values must now be set to the current values so that in the next iteration of the loop, the values contained within last_left and last_right will be correct. In fact, in theory, this program, this particular iteration is all we need. And as you can see in the terminal, we no longer have to deal with a large volume of data coming back from the Arduino. So that's great. But notice what's happening at certain places. What we're getting is a lot of repeated signals from the same sensor. And this is a phenomenon known as bouncing. Unfortunately, in the world of electronics, that's just how things are. Sometimes signals are just not that clean. And when it comes to, something like a sensor, you may sometimes get unexpected noise like this, which our program will end up interpreting as the pedal leaving and re-entering, and that's something we don't want. To fix this, we need to do what is known as debouncing. Now, there are many strategies to debouncing, and what we're going to use here is a software one, With just approximately 10 more lines of code, we are able to work around this problem quite well. Here's what we've done. Essentially, our entire strategy is based around the fact that, well, when your pedal actually enters the range of the sensor, it's not going to enter again for some time. That is, we're actually going to assume a little bit of delay before we see the pedal again. This tends to be a fairly good assumption because you can't pedal at lightning speed, and with this, we can effectively filter out all the bouncing because those tend to happen very quickly, one after another. To do this, we actually introduced two more variables to keep track of the last time we've seen the left and right pedals. We initialize them to zeros, and essentially, every time we encounter the same sort of condition, that is, when one of the sensors read high when it was previously low, that is of course, supposedly, when the pedal has entered the range of the sensor, we first do a time differencing to check the current time, right, that's what this function does, to check the current time against the previous time that we've seen the pedal. Only if the difference is greater than a threshold time we've set, which we have set up here as 400 milliseconds or slightly under half a second, that is the only time in which we actually send out the signal. Otherwise, we remain silent. We assume it's bouncing, we don't send a signal to the computer. Of course, if this was considered a valid entry of the pedal, then we will actually update the last seen time as well. This is of course extremely important, otherwise the entire debouncing mechanic will not work correctly. Of course, we repeat the same for the right pedal as well. The right pedal uses its own timing, and yeah, with this strategy, we can effectively eliminate the effect of bouncing. As you can see in the output, it's now very clean, right? You see left and then right and then left and then right. You no longer see a bunch of, say, lefts in a row or rights in a row. And that is exactly what we're aiming for. Now, what we've seen so far is as far as I want to take it for this tutorial, but what I have here is a sort of enhanced version that I will be releasing as well. This one just does something a little bit differently. Instead of using, our actual loop to detect when a pedal has entered the range, we're using Arduino interrupts instead. This is a slightly more advanced feature when it comes to the Arduino, and all we're doing here is, instead of having to check for ourselves when, the previous state is low and the current state is high, that means the pedal has come in, we let the Arduino do it instead. We use an interrupt routine to do this, and it basically detects the rising edge, which is the transition from low to high. So it's exactly the same thing. So yeah, no very big difference between this method and the method I've shown you previously, but this is how to make it, a little bit more fancy. What you're seeing right here is the code I have deployed to my so-called working or production version of the exercise bike program. This and all versions of code I've shown you previously will all be released for download, so you can study them at your leisure. So alright, now that we know for sure what messages are coming back from the Arduino, what we need to do now is to develop the software side of things, just a piece of code that runs on the computer that will send out the necessary keystrokes, as well as to, of course, display whatever GUI components that are necessary. The code that runs on your computer, the so-called client-side code, is extremely simple. And well, since I'm using Python here, as usual, everything just comes from a library. Now, the two libraries I'm using here is a serial library, as well as this library called PyAutoGUI. The former, of course, we need to talk to the Arduino, which is communicating with the computer via serial, and the latter is just there to press the up arrow key. Yeah, that's its only purpose, and of course, we are using this to advance Google Street View. So here's how this code works. We start by opening a connection to our serial port and setting the correct baud rate so that, well, the Arduino can communicate with the program. Then we set a count to 0. In an infinite loop, we simply keep checking to see if there are any messages waiting for us via serial. Basically, this in waiting will tell us how many bytes are sitting there waiting for us to read back. As long as this is greater than 0, that means, there is incoming data. What we'll do is we'll use readLine to read an entire message up until the new line character. Notice we're actually not using the value that comes back at all. We don't need it. Since we're sure that the only messages we're gonna see is either left or right, every time we see it, this tells us that we have paddled half a round. The idea is, as long as I've paddled 3 full rounds, we want to move forward once on Google Street View. So once the count reaches 3, we press up and reset our paddle count to 0. That's it, 15 lines, that's all we need to do. With this running, you can see the moving forward statement get printed from time to time. In fact, that is of course when I have made 3 complete paddles. Now, I'm not going to show you Google Street View for copyright concerns, but as you can see, as I'm paddling, the cursor in this page of code is actually moving up. And of course, that is because the program is generating an up arrow press. Of course, this isn't fun without a GUI, a graphical user interface, which is why now we bring in tkinter. Now, tkinter is a pretty popular Python library that actually does the GUI. So what you can do is you can use it to place things like buttons or labels on screen, and that's exactly what we're doing here. Now, this is the same code as we've seen just now, so well, I'm not going to go into too much detail. Notice of course that we've actually moved it out into a function. So what's really changed here is we've created a tkinter object which actually represents our window. We have set it to these dimensions, and then we've actually created 2 labels which we have packed into the window itself. So that's basically, how the syntax works. The first label is just a textual label that says total count, whereas the second one will actually display the count. Now, tkinter is really cool in the sense that you can create a special kind of variable, and you can use that to bind it to an element. Later on, within your actual logic, changing or setting the value of that variable will automatically update the GUI without any further work on your part. And yeah, that's really cool. That actually makes things really simple for GUI programming. What happens when you call the main loop function is that the GUI actually starts up and it starts doing its thing. The problem is, of course, this is a loop, and what that means is anything after it will not run until the window itself is actually closed, and we don't want to put our main logic after that. Which is why I've moved my logic to a function like this, and basically I've called the root.after function to run it. The idea is I want to run this function after a wait of this amount of time. Of course, since I'm not really waiting, it's going to run it immediately. So yeah, the logic is going to run, it's going to read from serial the same way we've done earlier on. But what's special about this is it ends by calling root.after again. So the idea is when main logic is done running, it's going to wait just a teeny bit of time before calling itself. This basically turns it into a loop because every time main logic finishes, it queues itself up to run again. So with this running in the background, as you can see, I can still control my cursor moving on the page, but as you can see, I now have this little window which tells me how many times I've actually paddled. And yeah, this is our first step towards building a complex GUI. Now, many of our functions concern time, which is why in the next iteration of this program, what we've done is we've imported a datetime library or module, which is what Python actually provides. What we're going to calculate here is basically the speed of paddling of the user. And we're going to just measure this in a very simple term, which is RPM, or rotations per minute. Essentially, to do this, we need to calculate the interval of time between each successive paddle. To start, we're going to create a variable called last timing. This is going to help us keep track of the last time the paddle was seen. And yeah, with this, we can calculate the interval of time in which the paddles are entering the scene. So, how we do it is this. Every time we encounter a paddle, we will check to see the difference in time between the current time and the last time the paddle was seen. Now, unfortunately, this gives us an object which is a little bit difficult to work with, which is why I added this line to convert the information held within the object to a number. Now, this gives us a value in seconds, which is why this line is actually wrong, so I'm going to correct it here, pretend you didn't see that. The idea is, if the interval of time exceeds 1 second, it could clue us into the fact that the user has stopped and resumed, so we don't really do anything. But in all other cases, we can start to calculate the RPM of the user's pedaling. Now, because we have one sensor on each side, this interval is telling us how long it took for the user to go half around. This is why we multiply this value by 2 so that we are able to figure out how long they would take to make a complete revolution. Knowing this in seconds, we can basically divide 60 by that number to figure out how many revolutions will be made per minute. We set the value to GUI and then we update the last known timing. Of course, I haven't told you about the GUI part yet, but there is not very much to show here. Essentially, we've just created a new set of labels, pegged them to the root element, and this time the variable we use for show is a string variable instead of a numerical variable. So what we're doing here is, well, we're just packing the information into the string variable and having it display nicely to us via the GUI. As you can see, it works, it does its thing. As you can imagine, you can take this further and further to get a full-blown GUI, as I have here. So what I'm showing you here is my so-called production version of the program, which is essentially the same process but, repeated many more times in a more complex manner. I will also release the code for that, even though it's split over a couple of files and it's not that pretty to look at. Also, some of the calculations assume my height and weight, so your mileage may vary, literally. But yeah, I think you get the idea. With just a little bit of Python and Arduino code, we can get a full-blown physical controller for Google Street View that even gives you statistics via a graphical user interface. So yeah, as it turns out, this is a surprisingly simple project, and well, since I'm fairly happy with how my code looks, I will actually be sort of open sourcing this entire project, from the Arduino code to the Arduino setup, to the actual GUI part, right? All of it. I will be putting everything up on Bitbucket. You will find a link in the video description, and feel free to pull the code, do whatever you like to it. It has been a fun project, and it is one of my 2018 goals. I'm not going to say New Year's resolutions, even though that's what it is, to be more fit in this year. But I kinda still don't like going out and exercising, and I can't cycle, by the way. Interesting fact about me. So yeah, this would be a fairly good alternative to doing that. Of course, do note that this is not technically the right way to be using Google Street View. I have actually been sort of banned from the service before for sort of paddling for too long. Basically, the screen goes black and it tells you to refresh the page. So there is some kind of implicit quota or limiting going on. So yeah, use this with caution is what I'm saying. But yeah, it has been a very fun and rewarding project, and hopefully this will also help me on my goal to be more fit, which is always nice. Anyway, that's all there is for this video. Hopefully this has been an interesting project to be, working along with. Again, feel free to poke into the code, feel free to, build this yourself and give it a try. But yeah, that's basically all there is for this episode. I hope you've enjoyed the process. Until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.